Hello everyone, let's have a tutorial on lab 1. So in this lab we should consider a sphere around above the ground as such with radius 50 centimeter and the distance from the ground equals s, which is 50 centimeter at the beginning. Then we will change it to 10 centimeter, and the center of the sphere is at s plus radius. So for this purpose, we consider 2D axisymmetric as this way. In 2D axisymmetric, we consider half of the sphere and the other half is considered automatically by COMSOL. Then this is the ground, which is in equals distance s from the sphere. For modeling this sphere in COMSOL, we put the half of the sphere this way inside a box. You should know the dimension of this box. So in my calculation, I consider 5 meter, but you should consider 10 meter as well. So we here, I consider 5 meter as one side, and but you should also consider 10 and 20 meters or whatever, and you should show the effect of increasing the dimension of these box and show its effect on the convergence of the calculation and select a specific value. So from now on I consider 5 meter and do the calculation for 5 meter. So in this problem, we used electrostatic problems as here, and we employ COMSOL or finite element method for solving this electrostatic problem. So let's open COMSOL here. So you should first select model wizard. Then when you open it, you have 3D, 2D axisymmetric, 2D, 1D axisymmetric, and more. So here, as I mentioned, we need 2D axisymmetric. I click on it. Then we should go to AC to DC. We are going to solve electrostatic problem. Then we should select electric fields and currents, electrostatic. Click on it or add it. Then we should go to study. Then here we should select stationary. We have some other studies like frequency dependent, time dependent, frequency domain, time dependent. So here we are in stationary. That's why I selected and done. We wait for it. Then we first define our parameters. Here A equals 50 centimeter, and S I chose capital S equals, if you select smaller s, since that is already defined in COMSOL, it gives you error. That's why I chose capital S. 50 centimeter. Then go to geometry. I select a circle. Radius is A. Sector angle 180 because you consider half of it. Center is Z equals S plus A. And rotation, let's don't change rotation and build all object. and we want this to rotate minus 90 degree. We want this to be this way, then you should click on this to have a full view. So this is the sphere that we modeled based on uh, lab 1. Then you should put this inside a square or rectangle or a box. So I select rectangle. I choose 5 meter times 5 meter. Corner 0, rotation, and here. This is our problem that we want to solve. But you should try other dimensions as well, like 10 meter, 20 meters, and see the convergence of your calculation. And then we consider this sphere as a PEC, perfect electric conductor. That means we should put the inside out or remove the conductor from inside. So here we select difference. We set whole geometry minus the sphere. We remove this part. Build all objects. That's why it's removed. Then we should select material. For material, we should right click on it, add material from library. Then we come to building, right click on air, add to component. Then it comes here, we should select the domain. It was already selected, so now I selected, it should come here. So we only have air because the sphere is PEC, and we already removed the inside. Then we come to electrostatic. So for electrostatic, we should select the ground, the boundary, and also the 1 kilovolt voltage on the sphere. So let's select ground. So this is our ground, and this is S, the distance between sphere and the ground. And we select this box as boundary. So this should be also ground because this is our boundary. We need it for if we want to solve electrostatic. Then we also need to consider 1 kilovolt on the sphere. So we select electric potential. We choose this boundary, put this on 1 kilovolt. Then we go to mesh. We select triangular. Then for the size, we select extremely fine. And since we want to solve this problem for a voltage on the sphere, and this area is more important for us, we choose a smaller or finer mesh size for this area. That's why I select boundary. I select this boundary, and first I put it on extremely fine. Then we can change the mesh size, select custom, maximum mesh size, I put it on this value. You can also increase it and decrease it and see the effect of changing the mesh. Then the next step is to save our model and then we run it. So let's save it. We save it as Q1 record. Then we run it from here, compute. And let's have a look at the question 1. It says plot the voltage distribution. So while it's running, we look at question. Yeah. So the first question asks for voltage distribution. This is voltage distribution as can be seen here. Electric potential, then surface electric potential. And for the next part, it says plot the magnitude of the electric field along the z-axis from 0 to s. Then it says what point in the space does have the strongest electric field. So for plotting electric field, we should go to results, 1D plot group, then we should select line graph, then so we want to plot something. We want to plot electric field on this line. So we should select x-axis and y-axis of what we want to plot. So y-axis should be uh, magnitude of electric field. So we select electric, and norm of E means magnitude of electric field. And for x-axis, so here we can select this. So x data is arc length that we selected. We said calculate the norm of E on this line from S equals 0 to S equals 2, from 0 to S. Then we plot it. You can see that electric field is maximum at 50 centimeter, this point, and it's minimum at the ground. So the question is, what is the maximum? So for the maximum, we know that this point is maximum, and that point is on the sphere. So the best way for calculating this maximum is to go to results, right click on it, or to go to drive values, right click on it, point evaluation. Then we know that this point is the maximum. We select this point, and we set to electrostatic, electric field norm. We want console to calculate a norm of electric field or electric field norm at this point. Then we don't need to, we just should compute it from here. When you compute it, the value appears. That's the maximum value. So next question. For part 3, it says plot the equipotential lines for V equals 0 to 1000 volts. So here we said 2D plot, then we right click, contour, and we said method levels, step from 0 with the step of 100, to 1000 volt, then it's on voltage, so we don't need to change it. Let's plot it first. So this is electric potential, but we want to have voltages on them as well. So to have the voltages, we check this one. So as can be seen, this one is 200, this one is 100, the box is 0, and we already selected 1000 on the sphere. That's question 3, equipotential lines. So question 4, it says how should the equipotential lines be if we desire a uniform field distribution. So here field is not distributed uniformly. That's why these distances are not the same between equipotential lines. So if we want to have if we have uniform electric field, these distances should be the same, and you should uh, prove it why these distances should be the same. You should show it by combining the formulas using what introduced at the beginning of the lab. So the question 5, it says reduce the gap to s equals 10 centimeters, solve the problem. For this one, I save another one. That one. So we have Q1 record. I name this as question 5 minute, just to avoid any misconception. Question 5 said first reduce the gap to s equals 10 centimeter, then solve the problem again. So this is question 5. We decrease s to 10, then we can come here. If I build all, this must come down because we decrease the distance. Then we can also compute it again, and it says what point in the space does have the strongest electric field, then what is the electric field at this point. So we come here, so we should plot 1D plot, right click, line graph, then should plot this line as well, magnetic of electrostatic, electric, then plot it. So we can see that the maximum electric field is at 0.1, which is on the sphere, and this value is something between these two. So we can again add point evaluation. We can select this point and electrostatic, then evaluate, which is this value. So if we compare these two values, record, you can compare them. The next part says that reduce the voltage so that the maximum electric field becomes equal to the maximum electric field in question 2. So we say in question 5, maximum electric field is 11,000 something. This is electric field, and the voltage is 1 kilovolt. It says which voltage we select for this case, that maximum electric field be the same as part 2, question 2. In question 2, maximum electric field is 3542. So how much is this value? You can calculate it as 311.5 volt. So what we should do, we should come to question 5. We should change this electric potential to 3115, and then we should compute it again. Then we should go to the question. It says what voltage should we apply in this case so that the maximum electric field for both values of the gap are equal. So we calculate it. It's then question 7, it says plot the magnitude of the electric field along the z-axis for this. Compare this plot with the plot of question 1. In which case do we have a more uniform field distribution? So now we have the new line plot. Then so I put the results of these both two cases here. You can see that both have the same maximum. However, the minimum value of question 7 is different from question 2, and the rate of change will be different, and you should decide which one have more uniform field distribution. Question 8 says plot the magnitude of the normal component of the electric field on the surface of the sphere for both cases. So for the first case, we add a new 1D plot, then line group, we select on the sphere, we choose electrostatic,